So what we're going to be looking at today is some trigonometry. And you might be kind of wondering, why are we studying triangles? What good does this do us? It can make sense to study areas, like what's the area, the floor space of a room, what's the volume of a swimming pool, or the volume of a tank on the back of a truck. These things can make sense, but why triangles? And the idea is that we can use triangles to find out the lengths, certain lengths that we can't measure directly. And we'll do an example today of where this goes. So first off, let's go back to the Pythagorean theorem. Now, the Pythagorean theorem applies to right triangles. And it's only with right triangles. So a right triangle is a triangle that contains an angle that measures 90 degrees. Now, it lets you find the sides, and it has this kind of a relationship. A squared plus B squared equals C squared. Now, the thing with the right triangles, this trick we can use to find the lengths of the sides of these things, it doesn't work on other triangles. You have to use different, there's two different rules you can use. There's the law of sines and the law of cosines, which are a little more complicated, but you can still figure out the sides of the triangle. This one, the simple version, only works for right triangles. Now, the other thing with right triangles is we use them to come up with our trigonometry. So we typically use a Greek letter called theta. And it's sort of like an O with a little curly Q in it. So use that to represent angles. Now, the thing with this trigonometry is we're going to label the sides of the triangle relative to where the angle theta appears in the triangle. Now, there's one side that's always consistent, and that's called the hypotenuse. The hypotenuse is always the side across from the 90-degree angle. So for this triangle, same thing. So hypotenuse, always the side across from the 90-degree angle. Now, the next side is called the opposite. And the opposite is the side across from the angle we're interested in. So this would be the opposite to this angle. And to this angle, this is going to be the opposite. Now, lastly, we have what's called the adjacent. Now, the angle has two adjacent sides. These are the sides of the triangle that form the angle. Now, one of these sides is already labeled as the hypotenuse. It's the side across from the 90-degree angle. So the other side, by default, becomes what we call the adjacent side. So for this angle, this is the adjacent. It helps form this angle, and it's not the hypotenuse. On this one, this is the adjacent. Again, this side helps form the angle, and it's not the hypotenuse side, which is already taken up. So this is where we get this idea of hypotenuse, opposite, adjacent. Now, using this understanding of how we label the sides of the triangle, now we come up with our trigonometric functions. And what they are, they're fractions made using the sides of the triangle. They're fractions made from the sides of the triangle. And they have some fairly particular definitions. The sine of the angle theta, it's always going to be the opposite over the hypotenuse. So whatever those sides measure, like let's say the hypotenuse is 5 and the opposite, say, is like 3, then you just take 3 over 5. That would give you the sine of that angle. And we'll do some examples with these. The cosine of theta is the adjacent over the hypotenuse. Then there's the tangent of theta. And that's the opposite over the adjacent. So there's a mnemonic for remembering these. It's called SOHCAHTOA. And so what it stands for, the sine is opposite over hypotenuse. Cosine, adjacent over hypotenuse. And tangent, opposite over adjacent. So it's a little trick for remembering these. Now, there are some other ones. It's not just sine, cosine, and tangent. There's 3 others, and they're basically variations of this. So there's cosecant. Which is hypotenuse over opposite. So basically you take sine and flip it, and you get cosecant. There's secant. Excuse me. Oh, excuse me. So it's hypotenuse over adjacent, or you just flip the cosine function. Then there's cotangent. Which is adjacent over opposite. So cosecant, secant, cotangent. And it's the same, this one here, if you flip tangent, you'll get cotangent. So that's what these mean. So the idea here is that once you have a triangle, you want to identify these sides, and then you can figure out the sine function, the cosine function, tangent, and so on, for some angle theta, using the ratios of these sides. So let's do this. Theta here, and let's go. Let's say a triangle like this. So if we want the sine of theta, well, again, it's going to be the opposite over the hypotenuse. So I'll abbreviate opposite. And then same with hypotenuse. So it's going to be opposite over hypotenuse. Well, in this case, that's going to be well, the hypotenuse, first off, it's always the side across from the 90-degree angle. So this side across from the 90-degree angle, that's 10. So we're going to have a 10. And then, as for the opposite, this is the side opposite the angle. So here's the angle. The side opposite is 6. And so we're going to reduce this down. So 6 over 10, 3 over 5. The way you can get that, both these numbers are even. You can divide them both by 2, give you an answer in those terms. So that's how you find the sine. What about cosine? Well, again, you've got hypotenuse on the bottom, and you have adjacent on top. So the hypotenuse is still 10. And the adjacent, well, this is the opposite. It's across from the angle. Hypotenuse is always across from the 90-degree angle. So the only side that's left is the adjacent. It's the one side that helps make this angle that's not a hypotenuse. So this means the adjacent is 8. And again, you can divide both of these numbers by 2 and get 4 fifths. Last one. I'm just going to do sine, cosine, and tangent. So it's opposite over adjacent. So what this comes out to, the opposite was 6. The adjacent was 8. And so this will reduce down to 3/4. Questions about that? All right. So that's the idea of the trig functions. You're just taking ratios of those sides. You just want to know how to label your hypotenuse, your opposite side, and your adjacent side. And these sides, the opposite and the adjacent, will switch off depending if your angle's here or if your angle's up here. If the angle's up here, this will become the opposite, and this will become the adjacent. All right, questions about that? All right, so let's see here. Let's say we have something like this. We've got this triangle. Well, again, we can try to label the sides, and this doesn't hurt. So across from the hypotenuse, I'm sorry, the 90 degree, that's your hypotenuse. The side across from the angle will be your opposite. And then this side here that's helping create this angle, but it's not a hypotenuse, that's your adjacent. Now the problem here is we're missing the opposite. So what we got to do is use the Pythagorean theorem to find that missing side. So the Pythagorean theorem says is that the hypotenuse squared is equal to this side squared plus this side squared. So for now, let's just call this x. It's going to be a number, we just don't know which one. So this means that 3 squared plus x squared will equal this hypotenuse squared. And again, the hypotenuse is always by itself. So we'll get 9 plus x squared equals 49. And we want to get x squared by itself, so we'll subtract 9 from both sides. And x squared equals 40. So what we do now, if we have a square, we take the square root. And again, we're going to take the square root of both sides. So you could cancel the square root and the square. They act like inverses. Now, if you take the square root of 40, what you're going to find out is that it's not a square root that's going to be very friendly. In other words, it's going to have this infinite decimal that goes on and on. Actually, that's kind of cool, to be honest. That's called an irrational number. So it's friendly when you get to know it. And we could just leave it like this. When we take the square root of a number and we get an infinite sequence of digits, we just say, forget it, we're just going to leave it like this. So that's one thing you can do. Now, what they do in the text, though, they're going to use this trick. And I want to show you this sort of special trick they use in the text. If you have two numbers, a and b, We're going to multiply together underneath the square root. It's equal to square root of A times square root of B. Another way of putting this, for example, we can take 8, rewrite it as the square root of 4 times 2. Rewrite that as the square root of 4 times the square root of 2. Now, why would we do that? Well, what we try to do, we break this up into a multiplication. The reason I chose 8 times 4 instead of like 8 times 1, I want to break it up so one of the numbers has a square root that's a whole number. So you want to be a little strategic with this. For example, if this was the square root of 12, instead of doing the square root of 2 times 6, I would do the square root of 4 times 3 because I can take the square root of 4. So what this means, square root of 4 is 2. This one will stay. So we get, and to be a little more complete with this, it's really 2 times the square root of 2. The way we write this, we'll just put it as 2 square root 2. So when you see this in the textbook, and this is going to come back later, they'll do this when we get to like quadratic equations. When you have a square root of something like 40, see if we can break it up into the product of 2 numbers, and then that product, each number inherits a square root sign. And one of those numbers might have a square root that's a whole number. So in the case of square root of 40, let's go back to this. We can write this square root of 4 times 10, or the square root of 4 times the square root of 10. See, they both inherited a square root sign. Square root of 4 is 2. So we'll just write 2 for this one. We'll just leave square root 10. I'm just going to circle it. But that's how they're getting these things. It's a little pedantic. As far as I'm concerned, this would work just as well, but for your homework, they're going to want you to go through these extra steps. So what we discover is that x is 2 times the square root of 10. So let's take a look at our triangle. And again, this is the hypotenuse. This one's the opposite. And this one's the adjacent. So sometimes before you can do anything with these trig functions, you've got to find all the missing sides to the triangle first. And then we can do something with the trig functions. Now, we did sine, cosine, and tangent last time. Let's shake it up a bit. Let's do cosecant, secant, cotangent. So the cosecant of theta, well, that's the hypotenuse over the opposite. So you're going to get 7 over 2 root 10. Now, let me see how they want you to answer these. Okay, so I'm going to leave it like this. Well, we could talk about rationalizing a denominator. I'm going to leave it like this for now. I'm not going to rationalize the denominator. If that comes up, I'll let you know. But for this course, I think we're just going to stick with this for now. I'll mention what that is later. So secant theta that's hypotenuse over adjacent. And so that's going to be 7 over 3. Finally, cotangent. That's adjacent over opposite. Which is 3 over 2 root 10. So again, we just use those definitions for the trig functions, and then we can get them to just take the ratios. So let me do one like this. Now I will mention that rationalizing of the denominator. And as far as numeric values go, it's not necessary. What you use it for, it can help if you're combining different fractions, and having a radical in the denominator of a fraction can be a little difficult. But there's an idea like this. So this is an extra thing. If we take the square root of a, multiply it to the square root of a, you just get a. The reason is that you actually get that whole relationship between a square and a square root. So what's going on in the background? Something times itself. Is that something squared? And then, of course, the square and the square root cancel. And that just gives you a. So that's why we do that. So one way to get rid of a radical or a square root in a denominator, so let's say you have this. You multiply top and bottom by a square root of 10. And the thing with multiplying and dividing with fractions, when you're multiplying and dividing, what you do to the top, you got to do to the bottom. What you do to the bottom, you got to do to the top. Remember, 2 square root 10 is 2 times square root 10. So you get 3 times square root 10. I'll use a dot here. And then 2 times square root 10 times square root 10. These will become just 10. So we get 3 square root 10. Again, we leave out the multiplication. 2 times 10, or 3 square root 10 over 20. So that's something I don't think that is an issue in this class. If it comes up, I'll go over this again. But this is what they call rationalizing the denominator. Again, I don't think you're going to have to do it, but if it does come up, we can revisit it. So let's see.
Let's say if we're in a situation where we need to simplify this and like we don't have the little square root sign in order to simplify it, what would you recommend on how to
Now you
write
see,
it?
if you don't have a square root sign.
Yeah, like if like on the homework it didn't offer like the square root sign, do I just like square root it and simplify it?
There should be a square. Oh, I see. There should be a square root sign. There should be a button you can press that lets you insert a square root sign. Like there's a little symbols button, and one of the symbols will be a square root.
Awesome. Okay, thank you.
No problem. Yeah, you'll get some symbols, and this again, it'll come back. We'll see this again with quadratic equations. We are going to have answers with square roots in them. Yeah, there should be a button next to where you enter your answer. Click on that button. There should be some symbols. And in those symbols, there should be a square root sign. So let's take a look at this. Let me see, maybe if there's one from the homework I can pull here. I think they have one. So I'll do this one. So I'm going to do this. Change this a little bit. So one of the things I mentioned is that why do we mess with these triangles? What are we accomplishing? Well, on your calculator, you actually can compute the tangent, cosine, sine, and actually all the other trig functions. I can show you how to do that of an angle. And I think what they use something I think called a Taylor series to come up with this. That might not be correct, but there's a way you can use a calculator to come up with, say, the tangent of 26 degrees. And let me show you where I'm going with this. Let's say we want to solve for side A. Now this is 24 meters, so this is a pretty far distance. And A is some, say, like the side of a building. And for some reason, let's say you don't have access to a long enough tape measure, you don't have any sort of ladders or anything, you can't get on the roof of the building. So how do you measure how high it is? Well, let's say you're able to figure out, say, if you're a distance of 24 meters from this building, if you were to look up at this building, so if you put your head on the ground and look up at that building, you can make an angle of 26 degrees and be looking at the very top of that building. Have like maybe like a little scope or something to make it a little more precise. And you want to figure out how high this building is. So what we have is this. This side here is opposite that angle. This here is the adjacent, because this is the hypotenuse. It's the side across from the 90-degree angle. And so the adjacent, well, it's this other side that's helping make this angle. So what we can do, we want to solve for A here. This is what we can do. Using what we have to work with. We have one unknown, we have a number, and a number. So the tangent of 26 degrees, the tangent of this angle uses the side we want to find and the side that we have. So we'll say this is A, over 24. And the tangent of 26, now we might say we have no idea what that is. That must be an unknown. Actually, it isn't. We're going to treat this, whenever you have the trig function of an angle, that we know the angle, this is a number we actually know. This is the unknown, that's a number. So numbers, one unknown, we can solve this. Now the thing is, tangent of 26 degrees, that's in your calculator. Now one thing you want to do with tangent of 26 degrees, you want to make sure your calculator is in degree mode. So if it's not in degree mode, it's going to give you the wrong answer. So that's going to be a key thing. So with a calculator, let me see, am I in degree mode? Yes, I am. So if we type in tangent of 26 degrees, we'll actually get this value. The calculator can come up with these. In ancient days, what you would do is you could say keep like scrolls or papyri, and you record, say, the tangent of 26 degrees, the tangent of 25 and a half, the tangent of 25. You have these large charts that have all these tangents and sines and cosines, or at least sines and cosines. And well, then you could use those to help figure out the heights of buildings. So if we find A, we're going to find the height of this building. And the thing is, the tangent of 26 degrees, it's always the same, no matter the size of the triangle. The 26 degrees is now. So what we're going to do, we'll multiply both sides by 24. We have that. So we need the tangent of 26 degrees. So the tangent of 26 degrees, you type that into your calculator, you get kind of a funky number. Now again, it's an irrational number. These are always really cool. They're kind of neat. That's a whole other story. But if you take this number, multiply it to 24, is 11.705582 equals A. It's actually approximate to A. And if we round this to the hundreds place, we'll get A is approximately 11.71 meters. So that's actually pretty high. But what the point is, it lets you measure the size of this, the height of this building, and you don't have to climb or scale it or anything like that. So let me do another example like this. So any questions about that? All right. So let's say we're going to find the height of the flagpole. Now what's going on here? Let's say this flagpole is casting a shadow. And this shadow is 62 feet long. Now we don't know the height of this thing. So we're going to call it h. And let's say we're able to figure out that the angle, if you go to the end of this shadow, take like a little scope, put it on the ground, and focus that scope to the top of that flagpole, you get 34 degrees. So how do we find the height of this flagpole? Well, again, let's look at what we have to work with. This is the hypotenuse. This is the side opposite, and then we have a number for the adjacent. So we're talking opposite and adjacent, so we're talking tangent again. So the tangent of this angle well, we have opposite and adjacent to work with, so it's opposite over adjacent. Now to solve for h, we're going to multiply both sides by 62. Now there's a habit in algebra not to write the multiplication if you don't have to. So you oftentimes, there's really an implied multiplication there. So if we do 62 times the tangent of 34, if we round this to the nearest hundredth, you get approximately 41.82 feet. And that's going to be your answer. Questions about that? So, one other thing they mention in this text, so that's how we can use triangles. Before I get into that other thing, that's why we're interested in triangles. It lets us find, let's say, like the heights of things that, I mean, it's kind of hard to climb up to a flagpole, get to the top of it. So you could come up with that using very careful measurements. A neat trick you can do, and if you back up to where the angle between, say, if you're lying on the ground and looking up at the top of something is 45 degrees. So this is kind of a pro tip. Let's say you have some tree. And it's got some kind of height. If you back away from this, so the angle from the ground to the top of that tree is 45 degrees, then the distance from this point, say to where the middle of the tree would be, this is the same as the height. Why is this true? Well, let's say this height here, we say we know this is 100 feet. This is going to be a really tall tree. So you'll get your tangent, 45 degrees, opposite over adjacent. Multiply both sides by 100. You'll get 100 tangent, 45 degrees is h. Put in my multiplication. The key thing here is the tangent of 45 degrees is equal to 1. So as a trick, if you can't, for any reason, compute like the tangent of 26 degrees or something like that, you want to try to find the height of something, back away from it until the angle from say a line that goes from the ground, say where your feet are standing, to the top of that object, that this angle formed is 45 degrees. That means the distance from where you're standing to the base of that object will be the height of that object. So this little trigonometry trick. Anyway, moving on. All right. So we're going to look at what are called inverse functions. So the idea is this. Sometimes what we're interested in is the angle. We want the angle theta. So if we have, say, cosine of theta is equal to the adjacent over the hypotenuse, the way we find theta is that theta will be the cosine inverse. And again, this is a button on your calculator of the adjacent over the hypotenuse. So this is kind of what happens. You take your angle theta, it goes into a trig function. And what pops out is some number. Opposite over hypotenuse, adjacent over hypotenuse. You'll get some kind of number. But with an inverse trig function, we start with that number. And then we get the angle theta. So it just does everything backwards. So for example, let's kind of go back to that tree example where we have a tree of a height 100 and we have a distance from the base of 100. This is our angle theta. Well, again, we want to know the sides of our triangle. So we have a hypotenuse. This is the opposite. Here's the adjacent. So the reason I know I'm going to use a tangent instead of a sine or a cosine, well, I've got opposite and adjacent to work with. So that's all I can really do. To use sine or cosine, I need the hypotenuse. Well, I could use the Pythagorean theorem to find out what that is, but a little more work, so I'm not going to bother with it. But you could do it. So the tangent of theta opposite hypotenuse and so you get 1. So what we have is the tangent of theta is equal to 1. So this is what we're going to do. Because the tangent of theta equals 1, then theta equals the tangent inverse of 1. And what's the tangent inverse of 1? Well, again, you can type this into your calculator, make sure it's in degree mode, and this will come out to be 45 degrees. And that's going to be our answer. So let me do another one. So the sine of theta is equal to 1/2. Find the angle theta. So the way we set this up, since the sine of theta is 1/2, this means that theta is the sine inverse of 1/2. And then you put this into your calculator, and there is a sine inverse on your calculator. On mine, I don't know if you can see this here. You can get this to the camera. Get a little closer. All right. So we got this sine button here. This sine button, there's in gold, and it's probably hard to see, but it says sine inverse, a sine with a little -1 above it. So to use that, I'm going to hit Shift, sine. And so that gives me the sine inverse. So what I'm going to do, 1/2 is a decimal. You can represent that as 0.5. Close my parentheses. I hit equals. You get 30 degrees. Now it's 30.00 on my calculator, but that's just sort of a mode that it's in. So this will be 30 degrees.
What does it say right above on the top? It says sin, and then it says equals 1/2, comma, and then right beside it, it says, what does it say? Tan?
Oh, right here?
No, up at the top, on the top right corner.
Oh, find theta.
Oh, find theta. Okay.
Do I need to raise the camera or? But that's it. That's what you do. So let's see here. An example they have here. I'll pull one from the homework. So let's say we have this. And they use different letters for the angle. They don't just stick to theta. They'll use alpha. They'll use beta. Alpha is kind of a popular one. So you see, given the tangent of alpha is 1.588, find alpha. So same procedure. Tangent of alpha, 1.588. This means that alpha equals the tangent inverse of 1.588. And that's going to be about 57.8 degrees. So questions about that? So that's pretty much it. That's the section on trigonometry. Let me take a look. Let's see. So for section 9.1, I might, yeah, this one's going to be a little longer. I'll save it for Thursday. And then that'll finish us up for everything for the first test. So I've moved the first test till Monday. Just kind of give you maybe a weekend to prepare for it. But that's going to be it for today. Any questions about these, let me know. Other than that, have a wonderful afternoon.
I'll see you tomorrow or Thursday. Bye.
Awesome.
Thank you.